Hey friends, welcome back to the channel and to the 6th episode of the research paper summary. Today I'll be covering the paper TriggerNER. This is an ACL 2020 paper that I really enjoy reading. They introduce something called the entity triggers to improve the learning of NER models with less training data. In this video, I'll first cover the context and contribution of this paper. I will then briefly talk about the new NER annotation process that is required to annotate these entity triggers. I will then cover the trigger matching network, a model proposed by the paper to encode these entity triggers and use them for NER. And lastly, I'll finish up this video by sharing some of the experimental results. I hope that you'll find this video useful. Let's get to it. If you're new here, my name is Ryan. I'm a first-year PhD student based in London, and on this channel we share actionable insights on different topics in AI research, entrepreneurship and lifestyle design, encouraging us to take more actions and live a happier and more intentional life. If these topics sound interesting to you, consider subscribing. Recent development in NER can be contributed to neural network models, achieving state-of-the-art results. However, training these neural models requires a large amount of annotated data, which are both expensive and time-consuming to create. And so a crucial question here is, how can we train an effective NER model with less amount of annotated data? Well, in this paper, they introduced entity triggers into the traditional label annotation process. Entity triggers are essentially a group of words that help us humans recognize entities in a given sentence. For example, as you can see from this figure, Alice traveled a lot to X. The travel to, highlighted in red, is an entity trigger that helps us humans spot that X is a location entity. The authors believe that the combination of entity triggers and the standard entity annotations can increase the ability of NER models to generalize and therefore achieve a stronger NER model with less labeled data. Overall, the paper has three main contributions. The first contribution is that they introduced the concept of entity triggers and crowdsourced and released 14,000 annotated entity triggers on two popular NER datasets. One covers the generic domain and the other covers the biomedical domain. The second contribution is that they proposed trigger matching network to encode these entity triggers as well as to use them to identify new triggers in unlabeled sentences. The third contribution is that the trigger matching network only uses 20% of the trigger annotated sentences to achieve a comparable results to a model that uses 70% of normal annotated sentences in the Code NLL 2003 dataset. This showcased that the entity trigger concept can effectively train NER with less annotated data. Traditionally, the NER annotation process follows some sort of tagging schema, either the BIO or the BIOES schema. In an NER dataset, each token is tagged with a label, and that label tells A, is this token an entity? And B, if it is, what type of entity is it? Is it a location entity, person, or organization? The label also tells us whether this token is the start of an entity span or is within an entity span. Using the BIO schema as an example, if the token is the start of the entity span, it will get given the B tag, the beginning tag. If it's within the entity span, it will have an I tag, inside tag. So for example, Bob traveled to New Zealand. New Zealand is a location entity type. New within the New Zealand will get the B tag, B location, and Zealand within the New Zealand will get the I tag, the I location. And together they form the BI location for New Zealand. With the entity triggers, we now need to introduce a new annotation process on top of the traditional process. Here's what the paper has proposed. Here, as you can see, there are two entity triggers and one entity, the rumblefish. The entity trigger are annotated using the word indices of the trigger and the starting index of the entity. So for example, with the entity trigger on the left, we would have had, lunch, add, represented by word index 2, 5, and 6, and the starting index of an entity, which will be rumble at index 7. Adding triggers to our annotation process means that for our new trigger annotated dataset, each sentence will have A, the traditional tagging using either the BIO or BIOES schema, and B, the entity triggers that you are seeing here. Let's now talk about the modeling side, the trigger matching network. The goal here is to train an NER model using the trigger label dataset such that we achieve a comparable performance against a model that is trained on a much larger, normally annotated dataset. The trigger matching network has three components. Firstly, we have the trigger encoder to learn the trigger representations. Secondly, we have a trigger matcher, a matching module that helps us identify new triggers. And lastly, we have the sequence tagger, which uses trigger representations for entity recognition. There are two learning stages for trigger matching network. Firstly, they jointly learn the trigger encoder and trigger matcher. And secondly, they do learning for sequence tagging. Let's start with the first stage. Learning trigger representation and semantically matching them with sentences are both inseparable tasks. But why do we want to do that? We want to semantically match our trigger representation with the sentences because it's impossible for us to identify all the entity triggers. And one of the ways to alleviate this problem is to use existing entity triggers that we already have in our dataset and use them to identify new triggers on unlabeled sentences. For example, in our NER dataset, we might have the following entity trigger, had a great dinner at. We want to be able to use these existing entity triggers to capture similar unseen new entity triggers. For example, a new unseen entity triggers that is semantically similar to our previous example is had lunch at. In order for us to capture these new entity triggers, we need our triggers and sentences to match semantically, and we are doing this by using the TriggerNER module. And so the first stage is to jointly train the trigger encoder and trigger matcher using a shared embedding space. The word vectors first go through the by-LSTM to get the contextualized representation of each token in the sentence. These contextualized representations are then used to learn an attention-based representation of both triggers and sentences through the self-attention layer. And so through this process, we will get the final sentence vector GS and the final trigger vector GT. We then feed the GT vector into a multi-class classifier to predict the type entity, as we want to use the type entity to shape the trigger representation. The loss function here is LTC. Finally, to match triggers and sentences, the paper uses contrastive loss, with the idea that similar triggers and sentences should have close representations. To train our trigger matcher, we need to perform negative sampling, as we need both positive and negative examples to teach our model to generalize. The training here is optimized using the loss function LSM. Overall, the joint loss function of the first stage is the total of LTC plus LSM. The next stage is to learn the trigger enhanced sequence tagger. The goal here is to output the tag sequence for input sentences. Here on the right hand side, we have the most popular architecture for NER, the by-LSTM CRF model. First thing to note is that these two by-LSTM are the same by-LSTM. Using trigger matcher, we can compute the mean of all the trigger vectors that's closely connected to this sentence and incorporate this mean trigger vector as the query to our attention mechanism to create the final attention-based token representation. The attention-based token representation is then concatenated with the input tokens and feed into the CRF tagger to predict the tag for each token. Okay, now that we have finished covering the training process of trigger matching network, let's now move on to the inference process. During the training and testing process, we have the label entity triggers to help us predict entities. But what happens when we use the train model to predict entities on unlabeled sentences with no entity triggers for us to use? Here's what the paper has proposed. First, we will use the trigger matcher to compute the similarities between the sentence representation and the different trigger representation in our entity trigger set. By measuring the similarity, we can retrieve the triggers that are the most similar to our sentence representation. We select the top k nearest and compute the mean of the trigger vectors. The rest is the same as the sequence tagging process. We use the mean trigger vector as the query and produce trigger enhanced sequence predictions on unlabeled data. Let's now talk about the experimental results covering different analysis. Here's the results table. The first thing to note here is that using only 20% of trigger annotated data, Trigger Matching Network was able to deliver a comparable performance to the baseline model that uses 50 to 70% of traditional data. This huge improvement in model performance with less annotated data showcased the positive impact of entity triggers in NER datasets. The second observation is the Trigger Matching Network plus self-training. Here, what the paper did was they make predictions on unlabeled data and used those predictions as weak training examples to continuously train the model. The results show a slight improvement in F1 score. And lastly, the trigger attention gives us a better interpretability into the model's thinking and prediction. As you can see here, the trigger attention scores help the trigger matching network model to recognize entities, and it also gives us an idea of what the model is paying attention to make its final predictions. And that's it for today's video. If you like this video, be sure to subscribe, as I'll be covering more research paper summary video in the future. In the meantime, feel free to check out other videos on my channel. Thank you for watching. I'll see you guys in my next video.